These are the revision questions for P6. So the first couple would be foundation, and then the last couple are higher. So question 2 in the middle is for both papers. I've got a couple of highlighters as usual. I've got my calculator because I probably need to use that at some point as well. So let's get started. Question 1, water exists as ice, water or steam. Complete the sentences. Choose answers from the box. So in the box we've got ice, steam and water. The particles arranged in a regular pattern in a solid, whoops, so I would write ice, okay. Particles arranged close together but not in a pattern in water, and then move quickly in all directions in steam. Which will have the most internal energy? 1 kilogram of ice, 1 kilogram of steam, 1 kilogram of water. Well, I know that internal energy is the kinetic energy and the potential energies of the particles. So which one's going to have the most kinetic and potential energies? The steam. Which will have the lowest density? I know that density is mass over volume, and I know that the particles are furthest away from each other in steam because it's a gas, so therefore that will have the biggest volume for the same mass. So the image on the next page shows an iceberg floating in the sea. The iceberg has a mass of 11,200 kilograms. The volume of the iceberg is 12.0 meters cubed. Calculate the density of the iceberg. Use the equation. So it should say density equals mass over volume, but my printer for some reason has cut this off. So I'll just write that out here for us. Density equals mass over volume. So I have a mass here, 11,200. So I'm just going to substitute into the equation. 11,200 divided by the volume, which is 12.0. And then put that in my calculator. 933.3 recurring. Explain why the iceberg will melt. So the iceberg will melt because there is a temperature difference between the ice and the sea. Okay, so the internal energy of the ice increases, okay, because energy is transferred from the sea to the ice. Okay. Figure 1 shows a model of the particles in a liquid. Again, my printer's not done this, but on your copy you should be able to see it's just like this, but a bigger picture. So give 1 similarity and 1 difference. You would see in figure 1 if it showed the same substance as a gas. Okay, so what it's asking you about is being able to show particles in a diagram like this. If I had the same substance as this but as a gas, a similarity would be that the particles would be the same size, because we would use the size of the particle as a model for that particle. So the same size particles, okay, but they would be further apart. Okay, or we could say that they were not touching, or that there were fewer in the same space. So describe 2 limitations of the model shown in figure 1. So first of all, a recap. A model is something that we use in science to try and visualize or explain a concept that either is something that we can't see, or is too small or too big or too far away, or what have you. Okay, so we draw, for the particle model, we draw these circles to represent the particles. But it's not a perfect model, so we need to think about two limitations. So what doesn't it show that we know that particles do? So first of all, it doesn't show movement or vibrations. So we know that even solids, the particles vibrate around a fixed position. So it doesn't show the particles moving or vibrating, and that is a limitation of it. We can't see the forces between the particles, so those intermolecular forces. Another thing is that we know that particles aren't solid spheres. Solid spheres. Okay, and we know that because remember in P7, which we'll revise at a different point, we know that it's no longer the plum pudding model that we follow for the atom, it's the nuclear. Well, you need to know about Rutherford's evidence for a nuclear model. So we know that it's not a solid sphere, but the diagram that you just saw a few minutes ago suggests that it's a solid particle. Okay. So explain why substances have different melting points. So different substances have different forces between the particles. So different amounts of energy are needed. Break the forces. Some fire extinguishers contain liquid carbon dioxide. Suggest how carbon dioxide gas can be changed to liquid carbon dioxide without reducing its temperature. So how can we change a gas to a liquid without changing the temperature? This is by increasing the pressure. So remember that one of the things that we can say about a gas compared to a liquid and a solid is that gases can be compressed, so we can exert pressure on them and turn them into a liquid by moving them closer together. So now we have ice is heated at a constant rate. Eventually all the ice changed to a gas. Figure 2 shows how temperature changed over 800 seconds. So here we have a graph of temperature in degrees Celsius against time in seconds. What change of state occurs between 200 and 750 seconds? So let's think about this graph to start off with. So when the temperature is changing, the kinetic energy is changing. When the temperature is flat, the potential energy is changing, so therefore the state is changing. So at this point we would have ice, and then here it melts. Here we would have water, and then here it boils. And then here we have steam. Okay, so you could think about it. I mean, you also know it's water, and hopefully we know that water's boiling point is 100, so going across to here. So the change of state that's happening is boiling, or we could also say going from a liquid to a gas. The name of that change of state is boiling, but the state is changing from a liquid to a gas. So explain how figure 2 shows the specific latent heat of vaporization is greater than the specific latent heat of fusion. So specific latent heat of vaporization is the energy required to change 1 kilogram of a substance from a solid to a liquid. So where it's going from a solid to a liquid, and the specific latent heat of, vaporization from a liquid to a gas. Apologies. And fusion, we're going from a solid to a liquid. So how do we know there's more energy that's required to change this from a liquid to a gas than there is from a solid to a liquid? Well, if it's being heated at a constant rate, then we can see that this line is longer, so therefore there is more energy that is required to change the state of this substance. It does also say, though, use data from figure 2, so that means we actually need to refer to how many seconds that takes. So we could say that the time to change from a solid to a liquid is so it goes up to 100 seconds, but it doesn't quite start at the beginning. Let's say 80 seconds, because I think that starts probably about 20, is 80 seconds. And the time to change from a liquid to a gas is 200 to 750, so 550 seconds. Okay, so therefore more energy required to change from a liquid to a gas. Okay, so 1,695 kilojoules of energy is transferred to water at 100 degrees Celsius. Water at 100 degrees Celsius. The specific latent heat of vaporization of water is 2.260 times 10 to the 6 joules per kilogram. Calculate the mass of water changed into a gas at 100 degrees Celsius. Use the physics equation sheet. So the equation you would be given is E equals mL. E is energy, M is mass, L is specific latent heat. You would need to be able to pick that yourself from the equation sheet, but for ease, I'm just going to give it to you here. So we just need to substitute our values in, and then we're going to need to rearrange. So 1,695 kilojoules, which means that that's 1,695,000. Okay, you could also write 1,695 times 10 to the minus 3 if you were used to converting it straight, like the prefix into the order of magnitude. The mass is 2.260 times 10 to the 6. Oh, sorry, the mass is what we're finding out. Specific latent heat is 2.260 times 10 to the 6. Okay, so to rearrange this, at the moment we've got mass multiplied by 2.260 times 10 to the 6, so we need to divide by 2.260 times 10 to the 6. We need to do the same on this side, so we would do 1,695,000 over 2.26. So if we do that on the calculator, then we have 0.75. The figure below shows a simple model of the 3 states of matter. What is the correct equation to work out the density of a material? So this is an equation you need to learn. Density is equal to mass over volume. The student explains density to his teacher using the particle model in the figure above. His teacher says there are limitations to the model, give 2 limitations. So we've already sort of done this question earlier on, but it just goes to show why it's important to do practice questions, because there are a lot of bits of repetition. So we could say, again, so it doesn't show the movement or vibrations. Atoms aren't, well, we could say forces. Atoms aren't solid spheres. Okay, when the gas in a container with a fixed volume is heated, the pressure increases as the temperature increases. Explain why the pressure increases. So we need to explain why the pressure increases using like the particle model diagrams above. So let's just think about what gas pressure is to start off with. Gas pressure is caused by collisions. between the particles and container walls. Okay, so if there is an increase in temperature, causes an increase in the kinetic energy of the particles. Yeah, because the internal energy increases. Remember that the internal energy is a combination of the kinetic energy and the potential energy of the particles, and in this case, if the temperature is increasing, the kinetic energy is increasing. If the kinetic energy is increasing, then the velocity is increasing. Okay, and so therefore there will be more frequent collisions. So there's more collisions per second. So overall, so there would be a bigger overall force. And each collision has more force. And the reason for this is because every time there's a collision, there's a change in momentum for that particle. Now, you will only, we don't really talk about it in that respect really, except a much higher level, and we start to think about that in A-level physics in terms of explaining that, but each collision will have more force.